I asked students at Caltech in 1964, what is electricity? And as usual, the entire class, some of the brightest minds we had selected, sat in silence, looking at me as though the question were a trap. The strange thing is that we have been living in the electrical era for nearly 150 years, ever since alternating current was invented in 1888, since the first power stations lit up cities in 1882, since the incandescent light bulb appeared in 1879. Electricity has become something far too familiar. You are surrounded by it in the phone you're charging, in the refrigerator running all night, in the electric car on the street, even in the internet itself, born in 1969, the very thing you're using to hear me right now, so you think you understand it. Who doesn't think that? But whenever I ask what is electricity, people usually give a very confident, very concise answer. Oh, electricity is electrons flowing through wires. And I have to try very hard not to laugh. Not because the answer is completely wrong, but because it explains absolutely nothing. It's like asking, why does it rain? And someone replying, because water falls down. It's true, but it means nothing. This familiar routine, flipping a switch, plugging something in, watching a bulb light up, has made us forget that what's actually happening right in front of our eyes is a process so strange it defies intuition. Familiarity has hidden the mystery. And if you're willing to keep going with me, you'll see electricity is not at all what you were taught in school. It's stranger, more absurd, and far more beautiful. All right, let's do a small experiment, the same kind Stephen Gray did back in 1731 when he tried running electricity along a linen thread and discovered that something invisible was being transmitted. You don't need any complicated equipment, just a piece of plastic or some nylon fabric. Rub it on your clothing for a few seconds. That's all. When you do that, you've accidentally performed exactly what Benjamin Franklin described in 1747. Electric charge doesn't disappear. It only moves from one place to another. Electrons leave one surface and jump to the other, leaving one place with a surplus and the other with a deficit. Now bring that piece of plastic close to your arm, but don't touch it. Just bring it close enough. Watch the hairs on your arm stand up as though pulled by an invisible finger. That sensation, that eerie, gentle tug, is the Coulomb force, which Charles Augustin de Coulomb quantified in 1785 with an equation stating that two charges attract or repel each other according to an extremely precise law. What you're feeling is not a high school parlor trick, not some trivial phenomenon we usually ignore. You are directly interacting with one of the four fundamental forces of the universe. The electromagnetic force, the same force that holds atoms together, operates your nerves, and produces the light illuminating your face right now. No particle accelerator needed, no multi-million-dollar instruments, just a piece of plastic, and your arm is enough to reveal the foundation of the physical world. Now let me show you what really took physicists centuries to understand. When Charles Augustin de Coulomb published his law in 1785, he quantified the force between two charges with a simple formula that shattered perception, no less than Newton's law of gravity did in 1687. According to Coulomb, if you place two electrons exactly 1 centimeter apart, not an astronomical distance, just 1 cm, the repulsive force between them is about 0.5 times stronger than the gravitational force between them. To grasp how absurd that number is, 10,000, 1 followed by 42 zeros. In the observable universe, the total number of stars is only about 10,000. That means the electromagnetic repulsion between two tiny electrons is greater than the difference between a speck of dust and an entire galaxy. This is not literary metaphor. It is elementary physics, something you can calculate yourself with a pocket calculator. And this is when the question I've asked students year after year comes up. The question that sounds very simple but shakes every intuition you have. If electrons repel each other with that kind of force, why doesn't your body alone, containing roughly 10,000 electrons, explode into a cloud of charge? Think about it. 10,000 electrons is more than the number of grains of sand on the entire Earth. If even a tiny fraction of them were out of electrical balance, you wouldn't be sitting here listening to me. The fact that you're still intact is evidence that some mechanism in nature is operating with such exquisite precision that we once didn't even notice it. It wasn't until James Clerk Maxwell published his historic set of equations in 1864 that the world began to see the full picture. Electricity and magnetism are not two separate strange phenomena, as people once thought, but two aspects of the same entity, the electromagnetic field. Maxwell was the first to show humanity that electric and magnetic forces are different versions of a single unified structure, a language that nature uses to operate everything from atoms to sunlight. He even predicted that oscillations of the electromagnetic field would produce waves propagating at about 300,000 kilometers, that is light, meaning that what you call light, the thing allowing you to read these words, is actually just an electromagnetic field vibrating in a very particular way. And it is this electromagnetic force, not hardness, not materiality, nor anything we usually associate with matter, that actually governs the world you perceive every day. Chemistry? Just electrons jumping back and forth between orbitals, pulled and pushed by charges. Light? An electromagnetic field oscillating at the right frequency. The solidity of objects? Electrons in your hand being repelled by electrons in the table with such strength that the two molecular systems cannot interpenetrate. The transmission of nerve signals in your body? Sodium and potassium ions being pushed across cell membranes by an electric potential gradient. The truth is, every force you have ever felt in your life is electromagnetic. There is no exception. When you flip a switch, the force you use with your finger to push it is not mechanical force. It is electrons in your skin repelling electrons in the switch. When you stand on the ground, the weight you feel is not the earth pushing you up. It is electrons in the soles of your shoes repelling electrons in the floor. The electromagnetic force is so powerful that it makes what you call solid actually solid. It gives molecules their shape, proteins their structure, DNA its ability to fold without disintegrating. It determines the melting point of iron, the elasticity of rubber, the brittleness of glass. If the electromagnetic force were even slightly stronger or slightly weaker, just a little chemistry would not exist. Molecules would not be stable, and life, with all its complexity, could not appear. But back to the crucial question. If the electromagnetic force is so terrifying, if electrons hate each other with a force unhavdal, times stronger than gravity, why is your body still stable? Why doesn't the chair you're sitting on explode? Why doesn't the entire universe become a swarm of free particles flying apart? The answer, and this is where physics becomes almost magically beautiful, lies in the perfect balance between positive and negative charge. Matter doesn't explode because every electron is always held in check by a proton. An exact balance so precise that if the electric charge constant were off by even 1 part in a trillion, the universe as you know it would not exist. It is this near perfect electrical neutrality, this almost absolute cancellation, that holds the entire world together. And how does the universe not explode when the electromagnetic force between electrons is so absurdly strong, as we just said? This is when nature demonstrates one of the most subtle mechanisms humans have ever discovered: cancellation, or charge neutralization. Let's start with the simplest thing in nature, the hydrogen atom. It consists of exactly 2 components, a proton with charge plus 1e, and an electron with charge 1e. These two values are not approximately equal, not similar in magnitude. They are exactly equal to a precision of 18 decimal places. And the result is that hydrogen is perfectly neutral. No explosion, no repulsion, no collapse, just existence. This sounds so simple that people usually overlook it, but it is precisely why hydrogen and all matter can be stable. If the proton's charge were larger than the electrons by just 0.000000000000001%, hydrogen would never last longer than a few nanoseconds. But because the two charges perfectly cancel each other, the atom sits proudly still, as though nothing remarkable were happening. Now scale it up. In 1 cubic centimeter of air, there are about 2.7 cross-10^-, molecules, each containing dozens of electrons and protons. If just one in 10^, of those molecules had one extra electron, your room would have an electric field as strong as during a thunderstorm. If 1 in 10^, of had an extra charge, you'd have a small lightning bolt right in front of your face. But in reality, nothing. The air is completely neutral. Everything you see is neutral to such a degree that you forget it contains trillions upon trillions of charges constantly interacting. Nature doesn't just prefer balance, it demands it. This became clearest in 1913 when Niels Bohr proposed his model of the atom. Though the Bohr model was later superseded by quantum mechanics, it gave us an intuitive picture. Electrons do not crash into the proton like a stone falling to Earth. Instead, they occupy fixed energy levels where the attractive force and quantum confinement reach perfect balance. Somehow the electron finds the position where it neither falls into the proton nor escapes too far. It sits exactly where the proton and electron cancel each other's charge, making the entire atom a neutral entity. This neutrality is not an exception. It is the rule. All matter, from the glass of water beside you, to the keyboard you're typing on, to your own body, is neutral with astonishing precision. Your body contains roughly half those electrons. If even one of them were not canceled by a proton, you would charge up to the point that every step you took would produce a spark. If 1 in 10^, electrons were unpaired, you would become a continuous discharger. If the imbalance were any larger, trust me, you would no longer have the chance to ask, what is electricity? But every electron and proton in your body is perfectly paired, rendering you neutral to the point that you behave like an uncharged object, even though you are actually a seething mass of charges. And this is nature's greatest trick. The electromagnetic force is extraordinarily strong, but because positive and negative charges in matter almost perfectly cancel each other, you never directly experience their madness. When you place 2 books next to each other, you don't see them repel, not because the electromagnetic force is weak, but because each book contains a colossal number of positive and negative charges in perfect balance. If even a tiny fraction of electrons in one book were unpaired, the repulsive force between the 2 books would be so strong you'd need a forklift to separate them. If protons were in excess, they would attract each other with a force no tool short of a particle accelerator could overcome. But because of perfect balance, you place 2 books side by side and nothing happens. It looks as though no force exists at all. What's even stranger is that this neutrality doesn't happen because of some moral rule of nature. It happens because the structure of matter forces it to be so. Protons and electrons are particles of opposite charge, and because their numbers in matter are almost exactly equal, all matter becomes electrically invisible at large scales. This is extremely important. If the charge in the universe were unbalanced by even 1 part in 10^7, the electromagnetic force would overwhelm gravity, and the universe could never form stable stars, planets, or atoms. Everything would either explode outward or collapse inward, depending on the sign of the excess charge. Yet the universe we live in has existed for 13.8 billion years and maintains near-perfect neutrality everywhere. You, me, Earth, the Sun, the Milky Way, all are almost perfectly neutral. And that is the simple but profound reason the universe doesn't explode. Not because the electromagnetic force is gentle. It is the strongest force you interact with every day. Not because electrons are well behaved. They are wildly chaotic. But because positive and negative charges are required by nature to cancel each other, creating a fragile yet incredibly durable state of balance. Once you understand cancellation, you begin to see that the stable world you live in is actually a continuous, silent, never-ending miracle of balance. So if protons and electrons cancel charge so perfectly that they keep the entire universe from exploding, we are forced to confront an even stranger truth. You have never actually touched anything in your life. This may sound like a philosophical joke, but it is stark physics, confirmed by both calculation and modern experiment. Let's start with the simple. When you place your hand on a table, you think your skin is contacting the wood or metal surface. But the minimum distance between the electrons in your skin and the electrons in the table is still about an hair's in meters, 1/10 of a billionth of a meter. Electrons never allow other electrons to enter the space they occupy. Not because matter is hard like brick, but because the Coulomb repulsion is so overwhelmingly strong that it pushes everything apart. At the atomic level, contact does not exist. This was once only theoretical inference until 1986, when the atomic force microscope, AFM, was invented, and for the first time allowed humans to directly measure the repulsive force between two surfaces with no actual contact occurring. The AFM works by bringing an ultra-sharp tip very close to a material surface. When the tip approaches within a few angstroms, just a few parts of 10 Hz, the tip is repelled by electromagnetic force. On the graph, you never see a point where the two surfaces touch. You only see the repulsive force skyrocket. This is direct evidence that what you call touch is simply the electromagnetic field trying to prevent electrons from penetrating each other. Even at that tiny distance, there is no mechanical contact whatsoever. If matter truly touched, the AFM would behave like a needle stabbing into soil. Instead, it behaves like two magnets of the same pole, always repelled. And here's the part that upends intuition. More than 99.99999999999% of the volume of every atom is empty space. What creates the sensation of solid, hard, dense is electromagnetism, not matter touching matter. When you press your hand on the table, the electromagnetic field from the electrons in your hand overlaps with the electromagnetic field from the electrons in the table, and that field pushes back. Your nervous system translates that force into the feeling of touch. When you place a book on the table, not a single atom of the book sticks to an atom of the table. There are only trillions upon trillions of electrons pushing against each other to maintain a separation of 10 Hz, 1 Hz meters. That is the entire physics behind the solidity of matter. When you throw a ball to the ground and it bounces, you think the molecules of the ball collide with the molecules of the floor. No, they approach and are repelled by Coulomb force. When you stand on the ground, what you call weight is actually electromagnetism, pushing you up, opposing your attempt to push the electrons in your shoe soles downward into the floor. When you hold a cup, the pressure you feel, the thing that makes you believe your hand is grasping the object, is only electromagnetic feedback. You don't even touch the clothes you're wearing. When you lean back in a chair, you are floating above a sea of electrons, held by repulsive forces that make you think you are actually in contact. In reality, touch is merely a convenient illusion your brain invented to describe the electromagnetic signals your skin receives. When you press a computer key and hear the click, the only thing producing that sound is the rearrangement of electrons in the key and electrons in your finger. Even sound is electromagnetism translated into pressure waves. This leads to a chilling conclusion. Every contact force you have ever experienced, pushing, pulling, holding, pressing, lifting, is electromagnetic. There is no exception. The mechanical world you think is fundamental is actually the electromagnetic world running in stealth mode. And that is why the universe appears stable. Every repulsive force that keeps matter from collapsing is electromagnetic. Every force that holds molecular structures stable is electromagnetic. Every motion you make, from your first step in the morning to the last switch you flip before bed, is electrons in you repelling electrons in something else. So even though you believe you are touching the table, the chair, the doorknob, in reality, you have never come closer than 10 hearts and meters to any of those surfaces. You are a living being suspended within the electromagnetic force, supported, resisted, moved, and bounded by it. So if you have never actually touched anything in your life, and every sensation of solidity is just the electromagnetic force pushing you away, that leads to a much bigger question. What is matter really, beneath the hardness that intuition tells you exists? To answer, we have to go back to 1897, when J.J. Thomson discovered the electron using cathode ray experiments. Before Thomson, the atom was considered an indivisible solid sphere, but when he measured the deflection of cathode rays in an electric field, he realized that the negatively charged particles had to be thousands of times smaller than the atom. It was a direct blow to a belief that had existed for 2 millennia. The solid block turned out not to be solid at all, but a hollow structure containing charged particles. Then in 1917, Ernest Rutherford discovered the proton by firing alpha particles at nitrogen. Rutherford showed that the atom has an extremely small, extremely dense, positively charged nucleus, while the electrons occupy most of the volume outside. This radically changed how we understand matter. The atom is not a solid marble. It is more like an empty solar system, with negative charge surrounding positive charge. But even that model didn't last long, because as soon as we tried to apply classical physics to the microscopic world, everything fell apart. If electrons orbited the proton like planets orbit the sun, they would have to continuously emit electromagnetic radiation and spiral into the nucleus in a fraction of a second. Yet the world stands firm. So what does an atom really look like? The answer arrived in 1926 when Erwin Schrödinger wrote his famous wave equation. The electron is not a particle traveling in a circular orbit. It is a probability cloud, a continuous distribution of charge describing where the electron is likely to be found. The sets PD, orbitals you see in textbooks, are not paths, but shapes of the quantum electromagnetic field. The electron is not located at one point, nor does it move along any specific trajectory. It is a state of a field. The proton is not a little marble either. It consists of 3 quarks bound by gluons, and gluons themselves are excitations of the strong field. When you zoom in far enough, you no longer see solid stuff. You only see charged particles distorting fields. In other words, matter equals sign charge plus field. Nothing more, nothing less. The world you live in is not built from surfaces or solid blocks, but from arrangements of charge that cause the electromagnetic field to create stable energy levels. The hardness of steel, electrons forced into energy configurations, where electromagnetic repulsion produces an extremely strong counterforce. The softness of rubber, electrons in polymer chains, able to shift flexibly before repulsion pulls them back to their original position. The hardest natural substance, diamond, because septal orbitals lock the charge into a structure so rigid that electrons can hardly change position. In other words, every material property, elasticity, hardness, brittleness, thermal expansion, is not intrinsic to matter, but a consequence of the electromagnetic field within atomic structures. Look again at the table in front of you. It appears solid, sturdy, with a clear surface. But if you could look with quantum eyes, you would see only empty space and electron clouds. The surface is merely the region where electrons refuse to let other electrons enter. The air around you is the same. Every molecule in 1 cubic centimeter of air, about 2.7 quarts 10 to 7 molecules, is held stable by charge and field. Air is transparent, not because it has no color, but because the electrons in nitrogen and oxygen molecules do not absorb photons in the visible range. They only oscillate in response to UV and IR waves. Transparency is also electromagnetic. The light you see is photons, oscillations of the electromagnetic field, passing through a world that is almost entirely empty, which you mistakenly think of as matter. Even temperature, what you perceive as hot or cold, is just the degree of molecular vibration, and those vibrations are governed by the electromagnetic forces holding molecules together. So why does matter have shape? Because electrons and protons can only occupy certain allowed energy levels, and the electromagnetic field sculpts the space around them. To understand any object, you must understand what its electrons are permitted to do, what they are forbidden to do, and what shape the surrounding field forces them into. Look deeply at anything, and you get the same answer. Not steel, not wood, not plastic, but charge arranged into a stable field configuration. So when you hold a cup, you are holding an electromagnetic field. When you sit on a chair, a field is pushing you up. When you breathe, gas molecules touch your lungs, not through mechanical collision, but through electromagnetic fields repelling electrons. Chemistry, biology, solidity, color, smell, taste, sound, everything is electromagnetic. If matter is only charge and field, and there is no such thing as collision in the mechanical sense, we must re-examine one of the biggest misconceptions most people carry from high school. Electric current is not electrons rushing through a wire like water flowing through a pipe. That idea sounds reasonable, even intuitive enough that you can picture the whole process. Flip the switch, electrons from the source surge into the conductor, race through the wire, reach the bulb, and light it up. But physics does not operate according to your intuition. And if you're patient enough to stay with me, you'll see why this matters so much that it changes the way you understand the entire modern technological world. Let's start with the simplest thing, the drift velocity of electrons in copper wire, where the density of free electrons is about 8.5 Quatscher 10 quantum half electrons per cubic meter. You might think that when you flip the switch, electrons shoot through the wire like high-speed water. But the truth is that electrons drift at an average speed of only about 0.1 mm per second. Yes, millimeters per second. That means if an electron at one end of the wire wants to reach an outlet 1 meter away, it would take nearly 15 minutes. So why does the light come on instantly when you flip the switch? This is where mechanical intuition collapses, and the electromagnetic view begins to speak. When you close the switch, it is not electrons racing along the wire. It is the electric signal, or more precisely, the propagation of the electromagnetic field traveling at nearly the speed of light. In copper wire, that signal propagates at about 0.7 C, or roughly 210,000 kilometers per s. It is faster than any material object you have ever seen. But it is not electrons traveling. It is the change in the electric field surrounding the conductor, propagating from the point where you flip the switch to the bulb almost instantly. Like when you push a line of people standing shoulder to shoulder. The person at the front doesn't have to run the whole length. They just push the next person, who pushes the next, and so on. The push propagates quickly, even though each individual moves very slowly. Electric current is the propagation of electromagnetic force, not a stream of electrons traveling far. If it were truly electrons flowing like water, your light bulb would light up after tens of minutes, not instantly. Here's an analogy I often use with Caltech students. Imagine a long tube filled with marbles placed tightly against each other. You push one marble into the front end of the tube. The marble at the far end pops out almost immediately. Even though no marble has traveled the entire length, that is exactly how electric current works. The electrons in the copper wire are already there. They do not need to be pumped from the power source. When you create a potential difference across the wire, each electron pushes the next one through the electric field, and that force propagates along the wire at nearly the speed of light, lighting the bulb instantly. Notice, it is force propagation, not electron travel. And here is the point most people miss. Electrons in metal do not travel in a straight long path. They drift slowly, zigzagging, constantly colliding with the crystal lattice, undergoing thermal motion while being influenced by the electric field. They spend most of their time moving randomly at thermal speeds around n-half null, but the net directional drift caused by the electric field is extremely small. That is why, when you flip a switch in California, the LED on your desk lights up instantly, even though the actual electrons have barely moved a fraction of a millimeter. And this destroys the entire picture of current as electrons flowing through wire like water in a pipe. If you try to understand electricity with mechanical intuition, you will never understand it. Only when you think of electricity as a propagating change in the electromagnetic field do you begin to get it. There is a beautiful truth I love repeating to students. When you turn on a light, the energy does not travel inside the wire. It travels outside the wire, in the electromagnetic field. This is a direct consequence of Maxwell's equations and is central to all of electrical engineering. Every electrical device you use in life, phone, TV, computer, battery, electric car, operates because of fields, not because electrons travel from one place to another. Electrons merely jiggle slightly around their positions, but the field is what carries the energy. If you want to visualize this, imagine waves on water. The water molecules only oscillate up and down, but the wave propagates across the lake at high speed. Electrons are like the water, oscillating in place. The field is like the wave, carrying energy far away. And this leads to an even larger conclusion. Electric current is a field phenomenon, not a material one. You cannot understand electricity if you keep thinking in terms of water flowing in a pipe. Electricity does not flow. Electricity propagates, and it propagates not by electrons, but by the electromagnetic field, just like light, radio waves, Wi-Fi, or lightning. I once said something many students remember forever. You might think the electrons go very fast in a wire, but they do not. It is because of this misconception that so many people grow up without understanding the true nature of electric circuits. But once you accept that electricity is a field propagating near the speed of light, you step into the real world of electromagnetism. This explains why copper transmission lines can carry thousands of megawatts from Hoover Dam to Los Angeles without needing to push trillions upon trillions of electrons. Long distances, the field simply displaces electrons locally, and energy propagates along the field. It explains why, when you plug in your phone charger Electrons do not travel from your outlet all the way back to the power plant, hundreds of kilometers away. It explains why lightning can carry terrifying energy, even though electrons in the cloud only shift a very small distance. Everything makes sense once you abandon the flowing water picture and replace it with propagating electromagnetic wave. If electric current is not electrons rushing through wire like water in a pipe, but rather the propagation of the electromagnetic field near the speed of light, the next question must be, how exactly does the electric signal propagate? Imagine a line of people standing shoulder to shoulder, stretching hundreds of meters. You give a gentle push to the first person. That person does not need to run to the end of the line. They simply lean, pushing the next person, who pushes the next, and so on. The person at the far end feels the push almost instantly, even though no one moved more than a few centimeters. That is precisely how an electric signal propagates in a conductor. No electron travels from one end of the wire to the other. Only the change in the electric field propagates along the wire. In copper, the density of free electrons is about 8.5 quaternions electrons per cubic meter, an enormous number, so that even in a 1 centimeter length of wire, there are more electrons than grains of sand on all the beaches on Earth. Because there are so many electrons, each one only needs to shift an extremely tiny distance to push the next one via the electric field. And because the field can change at nearly the speed of light, the electric signal propagates extremely fast, about 0.7 C, or roughly 210,000, even though the actual electrons drift at only 0.1 mm per s. This vast difference is why the light bulb lights up the instant you flip the switch, even though the electrons themselves have barely moved a few micrometers. To picture it more clearly, imagine the copper wire as a tube packed full of marbles. If you push one extra marble into one end, the marble at the other end pops out almost immediately, even though no marble has traveled the full length. The push propagates. Matter does not need to travel. In a conductor, electrons are like those marbles, densely packed, jostling with thermal motion at about Nm1 cells, but with an extremely slow net drift. When an electric field appears, they shift slightly from equilibrium. That tiny shift propagates through the electromagnetic field. This is push propagation, the spreading of force, not the flow of particles. Unlike the line of people, where the push propagates mechanically through bodies, in a conductor the force propagates electromagnetically, obeying Maxwell's equations. When you flip the switch, you apply voltage across the wire, which means you change the electric field at one end. That change propagates not only inside the wire, but around it. The external field around the wire determines where energy goes. The wire merely guides it. A shocking but 100% true fact. Energy does not flow inside the wire. It flows in the space around the wire. Electrons in the wire merely rearrange to allow the field to exist. This sounds so counterintuitive that most people refuse to believe it until they study electromagnetism. But think of water waves. Water molecules oscillate in place, but the wave travels fast. Electrons oscillate in place. The field travels fast. When you plug in your phone charger, electrons do not travel from the power source through the cable to the battery. Instead, an electric field is established along the charging cable, forcing electrons near the battery end to redistribute, and energy enters the battery through the field, not through a marching column of electrons. This also explains why 60 Hz AC circuits work even though electrons only oscillate back and forth a few micrometers around their original positions. The electric signal exists because of the field, not because electrons go anywhere. Let's return to the line of people analogy, but make it a bit more complex. The closer they stand together, the faster the push propagates. In copper wire, electrons are extraordinarily dense. Each is surrounded by millions of neighbors. So even a tiny change in electric field is instantly felt and responded to by all electrons in the region. Even in superconductors, where resistance is zero, electrons form Cooper pairs, allowing the field to propagate perfectly without energy loss. The key point remains. In every case, the electric signal is the propagation of the field, not of electrons. Now imagine a familiar situation. You flip the light switch in the living room. Current does not run from the switch to the bulb, like particles flowing in a pipe. When the switch closes the circuit, the electric field in the wire changes instantly and propagates at nearly the speed of light. The moment the electric field reaches the bulb, electrons right there in the bulb are affected and begin to oscillate, heating the filament and producing light. No electron travels from the switch to the bulb. Every electron simply oscillates in place. Yet the entire circuit behaves as a unified system because the field propagates so quickly. This also explains why, if you cut a wire in half and put your hand on both cut ends, you do not feel electricity flowing through your body like water in a pipe. The electric signal is not a stream of matter. It is a language of field exchange. And the field only exists when there is a closed circuit to guide it. Once you understand this, you understand why high voltage transmission lines do not spray electrons into the surroundings and do not cause the air to explode as if particles were colliding. Electrons stay within the wire. The field surrounding the wire is what carries energy long distances. So if the electric signal propagates via the field rather than a stream of electrons flowing like water, the next question has to be, what exactly is voltage? This is a word every textbook mentions, but the way we are taught it in school often makes the concept vague and sometimes outright misleading. You are told that voltage is like pressure pushing electrons along. It sounds familiar, reasonable, and just enough to pass the test. But when you enter the real world of electromagnetism, that explanation no longer holds. To understand voltage, we must go back more than 2 centuries to 1800, when Alessandro Volta invented the first chemical battery, the voltaic pile. This was the first device in history to produce continuous electric current without friction or sparks. Volta stacked alternating copper and zinc plates immersed in electrolyte. When electrons separated from the zinc and moved to the copper, a potential difference was created. One end negatively charged, the other positively charged. And from that we called the difference voltage. But what Volta in 1800 could not know, and what James Clerk Maxwell's equations revealed in 1864, is that voltage is not pressure or energy carried by electrons, but a difference in the value of the electric field, encoded in a quantity called electric potential. In other words, voltage is not something that exists inside the wire. It exists in space as a field. When you are taught voltage is like pressure, you imagine 2 points with different potential, like 2 points in a water pipe with different pressure. So water flows from high to low pressure. The problem is, there is no water in the electric wire, and electrons cannot flow like a liquid. As we have said, electrons drift at only 0.1 mm per s. So the notion of pressure pushing electrons cannot be the true essence. Let us keep the pressure image, but replace water with something more accurate. Electric potential, an invisible field existing around the wire, created by the arrangement of charge. Think of it this way. If you stand on a hill, water flows downhill, because the difference in height creates a gravitational potential gradient. But water does not flow because it wants to. It flows because the gravitational field creates a preferred direction. In electricity, voltage is the height in a far stronger field, the electric field. When one end of a wire has higher potential than the other, electrons are not pushed by water pressure, but by the electric field that appears in the space around the wire. forcing electrons in the metal to shift slightly to balance the field. You do not see the field, but you see the consequence, current. This is why I never liked the textbook definition of voltage as energy per unit charge, even though it is mathematically correct. It is correct, but insufficient. It is like explaining gravity by saying it is an attractive force without ever mentioning the curvature of space-time. Correct, yet wrong. Close, yet missing the point. Voltage is the difference in electric potential, and electric potential is an indirect description of the electric field, the thing that actually produces force. You can picture voltage using the image of a pressure gradient, but only if you replace fluid pressure with the slope of an invisible field. Let us expand the example. Imagine a tilted plane. A marble rolls down, not because there is flowing water, but because there is a slope. Voltage is the slope of the electric field. Electrons roll downhill, not because someone pushes them, but because the field structure makes the new position lower in energy than the old one. In metals, free electrons are always drawn toward regions of lower potential. But here is the interesting truth. The electric field created by voltage exists outside the conductor, not inside it. The wire merely provides a place for electrons to rearrange. It is the external electric field around the wire that determines energy and direction of motion. This may seem abstract, but you see a familiar version of it every day. Lightning. Two clouds with different charges do not discharge because of electron pressure, but because the potential difference creates an extremely strong electric field in the air, until the field becomes so large that it ionizes the air and creates a conductive path. Only when the field appears does everything happen. Voltage does not gradually push electrons along the wire. It establishes the field configuration, and the field produces the force. Let me give you a more familiar picture. If you stand in a quiet room, you do not feel wind. But if you open a door between a high-pressure room and a low-pressure room, air rushes through instantly because of the pressure gradient. Voltage also creates a gradient, but not of air, of electric interaction. When you flip a switch, you connect two regions of different potential, and instantly the electric field propagates along the wire near the speed of light, forcing electrons near the bulb to shift. The bulb lights up, not because electrons from the switch ran to it, but because the field arrived. In other words, voltage is only how we measure the slope. It is not the thing that actually pushes anything. Just as a topographic map does not push you down the mountain, gravity does. Voltage does not push electrons. The electric field pushes electrons. Voltage only tells you where an electric field will appear when the circuit is closed. And this is where many people get it wrong. They believe voltage exists inside the wire, the way pressure exists inside a pipe. Voltage exists in space, in the form of a field, while the wire only influences how the field is distributed. If you change the shape of the wire, the field changes accordingly. If you bend the wire into a coil, the field follows it. Voltage is not a property of the wire. It is a property of the space around the wire, determined by the charge configuration inside the wire. Once you understand this, you immediately understand why bare copper wire does not necessarily shock you, but high voltage lines are dangerous even when you stand a few meters away, not because there are more electrons, but because the field around the wire is so strong. So if voltage is really the slope of the electric field, and it is the field itself that propagates the electric signal near the speed of light, then this is the moment we step into one of the greatest intellectual revolutions in the history of science. The marriage of electricity and magnetism, completed by James Clerk Maxwell in 1864. But to fully grasp the greatness of Maxwell, we have to go back more than 3 decades earlier, to 1831, when a man with wild hair and a curiosity so intense it was almost dangerous. Michael Faraday accidentally discovered something that changed the entire course of civilization. Faraday didn't know much mathematics. He was looked down upon by some scholars of his time because of his working class background. But he had something not everyone has: an extraordinary physical intuition and the ability to see the invisible. In 1831, Faraday wrapped a copper coil around an iron core, then placed another coil on the opposite side. He connected one coil to a galvanometer and the other to a battery. When he opened and closed the battery circuit, the galvanometer needle jumped wildly. There was no direct wire connecting the two coils, yet current appeared. Faraday had unintentionally proven a bewildering truth: a changing magnetic field creates an electric field. He called the invisible lines around the magnet lines of force, and although people at the time mocked the idea as a fantasy, Faraday believed they really existed, and that they were the bridge between motion and electrical energy. He had described the essence correctly. He just lacked one thing: the equations. And that is when Maxwell appeared. In the 1860s, Maxwell gathered all the experiments of Faraday, Ampere, Gauss, and many others. In 1864, he wrote down 4 simple equations that hit the old view of the world like a sledgehammer. Electricity and magnetism are not two separate phenomena. They are one. If the electric field changes, it creates a magnetic field. If the magnetic field changes, it creates an electric field. They cannot be separated. They are two faces of a single entity, the electromagnetic field. And what makes Maxwell one of the greatest minds of all time is his next discovery. When you combine those 4 equations, they predict something no one had ever seen before: electromagnetic waves that generate and sustain themselves, propagating through space. Maxwell calculated the speed of these waves and realized it was exactly the speed of light. He concluded light is an electromagnetic wave. I want you to pause for a second and feel the audacity of that conclusion. No one had ever seen electromagnetic waves. No one had measured them. There was no experimental evidence. Maxwell went from equations, and the equation said light is not some mystical entity. It is simply an electromagnetic field that is oscillating. If you change the electric field fast enough, you will create light waves. The entire universe is illuminated by electromagnetism. If Faraday was the one who discovered the invisible lines of force, then Maxwell was the one who proved they are not only invisible, but the foundation of everything you see. But this was still theory until 1887, when a young German physicist, Heinrich Hertz, performed an experiment that proved Maxwell was correct down to the last detail. Hertz created an electric spark between 2 metal electrodes, and he found that a loop of wire across the room, no connecting wires, also produced a spark. He realized he had created and detected electromagnetic waves. With extremely crude equipment, Hertz showed that the waves could be reflected, refracted, diffracted, just like light. He measured their propagation speed and found it matched Maxwell's prediction, nearly 300,000 kilometers per s. What Maxwell had predicted on paper had become reality. When asked about applications, Hertz just shrugged. None whatsoever. Fortunately, he was wrong. 8 years later, in 1895, Guglielmo Marconi used those very waves Hertz had produced to send the first long-distance radio signal. And in 1901, he transmitted a signal across the Atlantic. Radio, television, radar, Wi-Fi, Bluetooth, GPS, all are descendants of the electromagnetic waves Maxwell predicted. When you hold a phone in your hand and listen to a song playing from New York while you're in San Francisco, that is Maxwell. When you tune into an FM station and hear a voice hundreds of miles away, that is Maxwell. When you turn on a microwave, turn on Wi-Fi, watch TV, receive satellite signals, all of it traces back to those 4 equations from 1864. Now let's return to the question, how do voltage and current relate to electromagnetism? Faraday showed us that a changing magnetic field creates an electric field. Maxwell showed the reverse. A changing electric field creates a magnetic field. Electromagnetic waves, light, are simply electric and magnetic fields creating each other, propagating through space without needing wires. That means when you flip a switch to light a bulb, what is propagating from the switch to the bulb is not electrons, but a change in the electromagnetic field. That change extends from the wire into the space around the wire, controlling the electrons at the bulb. And all of it happens near the speed of light. When you connect the battery to a wire, voltage does not push electrons along. It creates an electric field along the path of the wire. That electric field is the electric part of the electric-magnetic pair. When electrons begin to move, they create a magnetic field around the wire, and that magnetic field in turn affects the electric field. In this way, electricity and magnetism merge into a single unified process. This is why I call Maxwell's discovery the greatest marriage in the history of physics. Maxwell did not merely describe electricity and magnetism, he unified them into one field. That unification later inspired Einstein, who used Maxwell's equations to deduce that the speed of light must be constant in all reference frames, paving the way for special relativity in 1905. To see it more clearly, try imagining a wire as a road and the electromagnetic field as wind. Electrons do not need to travel the road to carry energy. The wind, that is, the electromagnetic field, blows the energy from source to device. When the wind changes direction, electrons shift. When the wind is strong, electrons move more. But the energy is always carried by the wind, not by the electrons traveling. And that wind is precisely the electromagnetic field Maxwell described. A field that can oscillate, propagate, reflect, interfere, create standing waves, transmit information, carry energy, and connect all your electrical devices into one unified system. Voltage is just the slope of the field. Current is just electrons rearranging under the influence of the field. The electric field and magnetic field are two parts of the same equation. From hydroelectric dams, steam turbines, wind generators, to bicycle dynamos, all rely on one single principle that Michael Faraday discovered in 1831. A changing magnetic field generates an electric field, and that electric field forces electrons to flow as current. In his classic experiment, Faraday wound two coils around an iron core, one connected to a battery, the other to a galvanometer. When he opened or closed the battery circuit, the galvanometer needle jumped, even though the two coils were not electrically connected. When he moved the magnet toward and away from the coil, the needle jumped again. But when the magnet was stationary, nothing happened. So what created the current? Not the magnet, not electrons from the battery, but the change in magnetic flux through the coil. This is Faraday's law, the law that underlies every electric generator on Earth. Humanity understood this more deeply in 1884, when Charles Parsons invented the modern steam turbine. Steam heated to 600 degrees Celsius, pressurized to hundreds of bars, blasts through turbine blades, spinning the rotor at thousands of revolutions per minute. That rotor is directly connected to a generator, a gigantic block of metal with coils and magnets. As the rotor spins, the magnetic field spins with it. And when the magnetic field rotates, it continuously changes relative to the stationary coils around it, creating an induced electric field. That electric field forces electrons in the copper wire to move. Current is born. That's all. But that all changed the world. Let's zoom out to see the power of this principle in practice. Hoover Dam, operational since 1936, houses 17 Parsons-type turbines with a total capacity of about 2.08 gigawatts. Water from Lake Mead drops nearly 180 meters, rushing through the turbine blades and spinning rotors, weighing hundreds of tons like titanium flywheels. As the rotor spins, its magnetic field sweeps across the stator, enormous copper coils, and according to Faraday's law, changing magnetic flux electric field, appears electrons are forced to flow. Current is fed into the national grid. Here's the interesting part. Hoover Dam does not send electrons to your home in Los Angeles. The electrons operating the light bulb in your living room were already in the wires. What Hoover Dam does is create a varying electromagnetic field. That field propagates near the speed of light along the transmission lines and forces the electrons in your house to oscillate. The energy arrives via the field, not via a stream of electrons traveling hundreds of miles. And this is exactly why a generator never produces electrons. It only reorganizes the electrons that are already there. Another misconception we carry from high school is the belief that generators require permanent magnets. In reality, most large-scale power generators use field windings, coils supplied with direct current, to create the magnetic field. Rotor spins, magnetic field spins. Varying electric field in the stator, alternating current appears. Then a small portion of that electricity is rectified to DC to feed the field windings again. This allows very precise control of output voltage and is how every modern power plant operates. Physically, the mechanism is always the same. Whether you spin the turbine with steam, water, wind, or hot gas, you are simply changing the magnetic flux through the coil, and that change creates the induced electric field. Faraday's law, in short, EMF equals sign, d theta AT. The induced electromotive force is proportional to the rate of change of magnetic flux. The faster the change, the larger the current. This is also why pedaling a bike feels harder when the dynamo is powering the light. You are paying mechanical energy to sustain the changing magnetic field, and the current produced opposes you, according to Lenz's law. Even in industrial generators, when electricity demand rises, say everyone turns on air conditioning, the increased load makes the turbine heavier. To maintain rotation speed, the plant must burn more fuel or release more water through the dam. You are witnessing the direct interaction between mechanics and electromagnetism. Electricity cannot be generated without taking mechanical energy from somewhere. The deepest insight here is this: a generator does not create electricity. It only converts energy from one form to another. The original energy may come from gravity, from the kinetic energy of wind, from chemical energy, from nuclear reactions, or even from your own muscles. But all of it must pass through one single gateway, a varying magnetic field that produces an electric field. So if a generator turns motion into electricity by changing the magnetic field, then nature forces us to ask the opposite question: can electricity be turned into motion? And the answer, the one that has shaped all of industry, transportation, household appliances, robotics, and the future of electric vehicles, is a resounding yes. Not only yes, but spectacularly, elegantly, and in perfect harmony with everything we have discovered. Electricity plus magnetism equals sign motion. The story begins in 1832, when William Sturgeon built the first practical direct current electric motor. It was simply a coil placed in the magnetic field of a horseshoe magnet. When Sturgeon passed current through the coil, it rotated. At first glance, it looked like a child's toy. Current in, coil spins. But behind that innocent rotation lies one of the most powerful laws in physics, the Lorentz force, described by Hendrik Lorentz in 1895. The Lorentz force says simply this: a moving charge in a magnetic field experiences a force perpendicular to both its direction of motion and the direction of the magnetic field. That force is not small. It is powerful enough to drive every electric motor in existence. Imagine an electron moving. If there is a magnetic field B around it, the electron is deflected sideways according to the left-hand or right-hand rule, depending on convention. If electrons are flowing along a wire, and you place that wire in a magnetic field, the entire wire is acted upon by the Lorentz force. And if the wire is free to rotate, it will rotate. An electric motor is really just a sophisticated application of a very simple story. Current in a magnetic field produces force. Back to Sturgeon's coil. When current flows into the coil, electrons in the wire move. The external magnet creates a magnetic field. Magnetic field meets current Lorentz force appear one side of the coil is pushed up and the other pulled down. The coil begins to rotate, but Sturgeon still had to solve a problem. When the coil rotates half a turn, the direction of current relative to the magnetic field reverses, so the force reverses too, trying to push the coil back to its original position. To fix this, he added a commutator, a mechanical switch that reverses the current polarity at just the right moment, so the force always pushes the coil in the same direction. That was when the first stable DC motor was born. But do you know what's even more amazing? An electric motor and an electric generator are actually the same device, operating in two opposite directions. If you spin the rotor, you generate electricity. If you supply electricity, the rotor spins. This is not a design coincidence. It is a direct consequence of Maxwell and Faraday. One device, two directions, two faces of the same phenomenon. Now look at an everyday example. The fan in your home. You flip the switch. AC current flows through the stator coils, creating a rotating magnetic field. No mechanical parts are rotating. Just the magnetic field itself rotates. As that rotating field sweeps across the rotor, it induces current in the rotor. And according to the Lorentz force, the rotor is dragged along with the rotating field. You don't see the magnetic field, but you see the blades spin. In a vacuum cleaner, the principle is identical. Stator coils create a varying magnetic field. The rotor is swept along by the rotation of the field. No pistons, no gasoline explosions, no oil lubrication, just the electromagnetic field doing all the work that an internal combustion engine needs dozens of parts to accomplish. That is why electric motors are powerful, durable, simple, and highly efficient. It all comes down to the Lorentz force. To visualize it more clearly, imagine a straight wire segment placed in a magnetic field. When current flows through the wire, electrons inside are deflected perpendicular to both the current and the magnetic field. That force creates torque if the wire is bent into a loop. An electric motor simply consists of dozens or hundreds of such loops, arranged so that the net force keeps the rotor spinning continuously. The more loops, the stronger the magnetic field, the more powerful the rotation. This holds true for every type of motor, from toy motors, fan motors, washing machine motors, electric vehicle motors, to industrial robot motors. They all rely on one single action, making charges move inside a magnetic field. In other words, a motor is a generator running in reverse. A generator uses motion to create current. A motor uses current to create motion. Because of this beautiful symmetry, electric motors run smoothly, powerfully, and with very few failures. Now let's go a little deeper, still keeping it as simple as possible. Magnetic fields always want their lines of force to be straight and stable. When current flows in a coil, it creates its own magnetic field. If the coil's magnetic field interferes with the magnet's magnetic field, a force is produced. The strong magnetic field wants to rotate the coil to minimize the interference. That is motion. If you supply alternating current, the current reverses direction continuously, so the stator's magnetic field rotates. This rotating field drags the rotor along. No mechanical commutator needed. That is the AC induction motor, invented by Tesla, which powers air conditioners, elevators, water pumps, and millions of other devices. In an induction motor, the rotor receives no direct electrical connection. It rotates because the rotating field in the stator pulls electrons in the rotor, inducing current inside it. That induced current produces Lorentz force, making the rotor turn. Motion is transmitted through space by the field, with no mechanical contact. Here is a truth of almost unbelievable beauty. You can create motion simply by making a magnetic field rotate without touching anything. And that is why the electric motor became one of humanity's most important inventions. Look around your home. Ceiling fan, vacuum cleaner, blender refrigerator, washing machine, dryer, air conditioner, water pump, all are motors. All of them are moving electrons in a coil to create a magnetic field. The magnetic field moves air, water, objects, or even an entire car. When you press the button to turn on a fan, you are not sending any mechanical command. You are simply allowing an electric field to enter the coil. A rotating magnetic field is created. The rotor follows. The blades cut through the air, and you feel wind. When you turn on a vacuum cleaner, the motor spins at 20,000 revolutions per minute, producing suction stronger than any purely mechanical system of the same size could achieve. The miracle is that you don't need to understand the Lorentz force to use them. But once you do, you can never look at the world the same way again. Electric motors also teach us a profound lesson about unity in physics. Electricity generates magnetic fields, generate force. Force generates motion. Everything in a motor follows the perfect Maxwell. Lorentz loop, electric field, current, magnetic field, Lorentz force, motion, new magnetic field, a flawless chain with no gaps. An electric motor leads us to an even stranger device, one that doesn't rotate, has no gears, makes no engine noise, has no pistons or blades, yet controls the way energy flows through the global power grid, the transformer. This motionless piece of metal has the ability to make the coil on this side talk to the coil on the other side, without them ever touching, a form of invisible communication that if you lived in the 19th century, you would have called magic. But in modern physics, it is the purest manifestation of the induction law that Michael Faraday discovered in 1831. In his classic experiment, Faraday wound two coils around the same iron core. The primary coil connected to a battery, the secondary coil connected to a galvanometer. When he closed the primary circuit, the galvanometer needle jumped. When he opened it, the needle jumped in the opposite direction. When the current remained steady, the needle stayed still. This led Faraday to a world-shaking conclusion. Current is not transmitted from the primary coil to the secondary coil. What really travels is changing magnetic flux. No electrons crawl through the iron core. No electric rays leap across the gap. Only a changing magnetic field. And wherever a magnetic field changes, an induced electric field appears. This is the heart of the transformer. The first coil creates a changing magnetic field in the core, and the second coil has its electrons forced to move by that electric field, producing a new voltage and current. The transformer operates entirely through fields, and that is why it works so astonishingly well. No moving parts, no friction, no gears, no significant wear. It is a static device that nonetheless stands behind the entire energy system of humanity. The operating principle of a transformer rests on one simple yet profound truth. For electromagnetic induction to occur, the magnetic field must change over time. That is why transformers cannot work with DC. only with AC. This is the reason the late 19th century war of currents tilted toward Tesla and Westinghouse rather than Edison. DC systems could not efficiently change voltage, while AC could. When the primary current alternates at 50 Hz or 60 Hz, the standardized frequencies set early in the 20th century to synchronize the entire grid, the magnetic field in the core also oscillates 50 or 60 times per second. Each oscillation is a pull on the electric field in the secondary coil, forcing electrons there to move in step. Changing magnetic field-induced electric field new current is born, a perfect chain of cause and effect. To understand transformers more deeply, look at the turn ratio, the ratio of the number of turns in the coils. The induced voltage in a coil is directly proportional to the number of turns. If the secondary coil has twice as many turns as the primary, the voltage doubles. If it has half as many, the voltage halves. That is why a transformer can step 120 V down to 5 V in your phone charger, or step 10,000 V up to 400,000 V at a substation for long-distance transmission. Power is almost perfectly conserved. Higher voltage means lower current. Lower voltage means higher current. This is not a clever engineering trick. It is an inevitable consequence of Faraday's equation. V equals sign N dt T. More turns, more voltage, yet power remains the same. It is this principle that allows gigawatts of electrical energy to travel hundreds of kilometers over transmission lines with only a few % lost as heat. The iron core in a transformer acts as a highway for magnetic flux. It gathers the magnetic field lines from the primary coil and channels nearly all of them through the secondary coil, enabling transformers to achieve extremely high efficiency, 98% to 99% for large power units. Without the core, most of the magnetic field would leak into the air, and the transformer would become so inefficient it would be useless. The iron core turns the transformer into a device so powerful it can operate for decades with almost no maintenance. What makes the transformer an irreplaceable invention in the modern world is its ability to bend voltage at will. The national power grid depends entirely on the ability to step voltage up to hundreds of kilovolts for transmission, then step it back down to hundreds of volts for use. Without transformers, power lines would have to be as thick as water pipes to carry even a few kilowatts over short distances. Without transformers, there would be no cities, no high voltage lines, no internet, no industry, a motionless device that controls every energy flow in society. The most important revelation the transformer offers, one almost no one is taught in school, is this electrical energy does not travel inside the wires. It travels in the electromagnetic field surrounding the wires, as described by the pointing vector. In a transformer, energy is transferred from the primary to the secondary coil, not because electrons run through the wires, but because the electromagnetic field propagates through the core and the surrounding space. The primary coil generates varying electric and magnetic fields. The interplay of those two fields carries energy to the secondary coil, where the new electric field forces electrons to move and create current. No electrons travel from primary to secondary coil, just as there is no material voice passing between the two coils. Everything happens in the field, exactly as Maxwell predicted in 1864. Virtually every electrical device in daily life contains a transformer in phone chargers, audio amplifiers, microwave ovens, refrigerators, radios, speakers, and every substation you pass on the street. When you plug a device into the wall, a transformer is usually the first component to touch the incoming current, deciding how many volts and amperes the device needs to survive and function correctly. All of this stems from one experiment. Faraday performed one morning in 1831 just to see what would happen if he wound two coils next to each other. No one, not even Faraday, imagined that experiment would lay the foundation for the entire planetary power grid. No one expected that two motionless coils would become the world's energy coordination system. The transformer is the most beautiful proof that physics does not need to be complicated to be profound. One coil, another coil, one iron core, and a changing magnetic field. That's all. Yet from that grew the entire electrified civilization. Once we understand that a transformer allows us to change voltage like bending an invisible lever of nature, we finally have enough pieces to look at a structure greater than any single machine. The power grid, the nervous system of civilization, the thing that connects every power plant, every home, every city, every electric vehicle, every computer, every light bulb into one unified technological body. This system did not begin with a global plan, but in a small neighborhood in Manhattan on September 4th, 1882, when Thomas Edison flipped the switch at Pearl Street Station, the world's first commercial power plant. The plant burned coal to spin a DC generator and supplied electricity to 59 customers, a small number, but the opening act of an entire era. Edison believed direct current was the future, simple, understandable, easy to distribute over short distances. But there was one massive problem he could not solve. DC could not travel far because voltage had to stay low for safety. Current had to be very high to deliver enough power, and that caused wires to heat up and lose enormous amounts of energy. Edison tried to expand the DC network, but beyond a few city blocks, the losses became an economic nightmare. What makes the transformer an irreplaceable invention in the modern world is its ability to bend voltage at will. The national power grid depends entirely on the ability to step voltage up to hundreds of kilovolts for transmission, then step it back down to hundreds of volts for use. Without transformers, power lines would have to be as thick as water pipes to carry even a few kilowatts over short distances. Without transformers, there would be no cities, no high voltage lines, no internet, no industry. A motionless device that controls every energy flow in society. The most important revelation the transformer offers, one almost no one is taught in school, is this electrical energy does not travel inside the wires. It travels in the electromagnetic field surrounding the wires, as described by the pointing vector in a transformer. Energy is transferred from the primary to the secondary coil, not because electrons run through the wires, but because the electromagnetic field propagates through the core and the surrounding space. The primary coil generates varying electric and magnetic fields. The interplay of those two fields carries energy to the secondary coil, where the new electric field forces electrons to move and create current. No electrons travel from primary to secondary coil, just as there is no material voice passing between the two coils. Everything happens in the field, exactly as Maxwell predicted in 1864. Virtually every electrical device in daily life contains a transformer. In phone chargers, audio amplifiers, microwave ovens, refrigerators, radios, speakers, and every substation you pass on the street. When you plug a device into the wall, a transformer is usually the first component to touch the incoming current, deciding how many volts and amperes the device needs to survive and function correctly. All of this stems from one experiment Faraday performed one morning in 1831 just to see what would happen if he wound two coils next to each other. No one, not even Faraday. Imagine that experiment would lay the foundation for the entire planetary power grid. No one expected that two motionless coils would become the world's energy coordination system. The transformer is the most beautiful proof that physics does not need to be complicated to be profound. One coil, another coil, one iron core, and a changing magnetic field, that's all. Yet from that grew the entire electrified civilization. Once we understand that a transformer allows us to change voltage, like bending an invisible lever of nature, we finally have enough pieces to look at a structure greater than any single machine. The power grid, the nervous system of civilization, the thing that connects every power plant, every home, every city, every electric vehicle, every computer, every light bulb, into one unified technological body. This system did not begin with a global plan, but in a small neighborhood in Manhattan on September 4th, 1882, when Thomas Edison flipped the switch at Pearl Street Station, the world's first commercial power plant. The plant burned coal to spin a DC generator and supplied electricity to 59 customers, a small number, but the opening act of an entire era. Edison believed direct current was the future. Simple, understandable, easy to distribute over short distances. But there was one massive problem he could not solve. DC could not travel far because voltage had to stay low for safety. Current had to be very high to deliver enough power, and that caused wires to heat up and lose enormous amounts of energy. Edison tried to expand the DC network, but beyond a few city blocks, the losses became an economic nightmare. This is why the grid is called the nervous system of civilization. It reacts quickly, subtly, and must be controlled down to the millisecond. The circuit breaker you flip in your home is merely a signal sent into the electromagnetic field, and the field pulls energy from whatever power plant has excess capacity at that moment. Some of the energy you use may come from steam spinning turbines in an eastern state, some from wind in the Midwest, some from hydropower in the Pacific Northwest. And you never know and never need to know. The field takes care of everything. The United States currently has 3 supergrids: the Eastern Interconnection, the Western Interconnection, and the Texas Interconnection. Each is a separate oscillating system, a giant musical instrument that hundreds of power plants must play in perfect time. There are even moments when solar power in California creates surplus and drives electricity prices. Negative meaning power plants have to pay someone to take the electricity, because otherwise voltage and frequency would become unstable. This shows that the grid is not something we simply use. It is something that must be continuously maintained and cared for, like the circulatory system of a living body. At a deeper level, the grid is the perfect proof of the perspective I have tried to convey from the beginning. Electricity is not a flow of particles. It is the shape of a field. The grid does not transport electrons from New York to California. It maintains an oscillating field at 60 hertz, and that field forces local electrons to move and produce power. The electrical world operates not because matter moves, but because of the oscillating pattern of the field. When you turn on a light, you are announcing to the grid that you need a small portion of energy. The grid responds by ramping up generation from dozens of different power plants, all just to keep the 60 hertz frequency constant. No system is more complex, yet more beautiful, synchronizing thousands of spinning machines, each weighing hundreds of tons, spread across an entire continent, all vibrating to the same beat. A wire in your home, hundreds of miles from Hoover Dam, oscillates at the same frequency as the rotor of that giant turbine. The same field, the same music, That journey becomes overwhelming when we trace the path of energy backward from a distant dam to the light bulb glowing on your ceiling. And the first thing to remember is that it did not begin at Hoover Dam or Grand Coulee, but at a small but revolutionary hydroelectric plant in Appleton, Wisconsin in 1882, the world's first commercial hydroelectric plant, powered by the flow of the Fox River and a generator spun by a water turbine, producing a weak but groundbreaking alternating current that opened an entirely new path for humanity. That path today carries energy thousands of miles to every outlet in hundreds of millions of homes. When you flip a light switch and see 120V appear instantly at the outlet, it does not mean that voltage traveled from the power plant to your home in the blink of an eye. It means the electromagnetic field in the wiring around you has been connected to the oscillating field of the entire North American interconnection at 60 Hertz, and that field forces the electrons right there. Electrons that have been sitting in your home's wires for a very long time to begin oscillating and produce light. The journey truly begins at a power plant. For example, a hydroelectric plant in the Pacific Northwest. Water from the reservoir falls through penstocks, rushes into turbine blades, spinning the generator's rotor at hundreds of revolutions per minute. The spinning rotor sweeps its magnetic field across the stator, causing the magnetic flux in the coils to change continuously. According to Faraday's law, that change in flux produces an induced electric field, and the electric field drives electrons in the wire to form alternating current. The voltage at the generator output may be only a few tens of kilovolts, but to transmit it hundreds of miles without burning up the lines, we must reduce current and increase voltage, because line losses scale with Igua or observed. So a step-up transformer near the generator boosts the voltage to 115 kV, 230 kV, or even 500 kV. From there, energy does not travel inside the wires like water in a pipe. It moves in the field surrounding the wires, as described by the pointing vector, which shows that energy flows from the plant along the surface of the space around the conductors. High voltage lines stretch across forests, mountains, deserts, carrying an oscillating electromagnetic field rather than electrons. Electrons in the wires remain almost stationary, drifting very slowly, but their field propagates near the speed of light. When the energy reaches a regional substation, a transformer steps the voltage down to about 13 kV or 4 kV for urban distribution. Then another transformer near residential areas steps it down further to 120/240th V, suitable for household appliances. The transformer hanging on the pole right outside your home is the final link that delivers the voltage you use every day. Now comes the wonder that most people misunderstand. When you turn on the switch, no electrons run from the dam to the light bulb. There is no long current crossing the continent. There is no journey of electrons across hundreds of miles of wire. All you do is close a circuit, allowing the grid's electric field to be applied across the filament of the bulb. The electrons in the filament, electrons that have never left that tungsten coil, are forced by the 120V electric field to move slightly. The resistance of the tungsten to that electron motion converts field energy into heat, and the heat rises to about 2,500, 3,000 degrees Celsius, causing the filament to emit visible light. The bulb lights not because electrons traveled from another state to get there, but because local electrons are being driven by the grid's 60 Hertz oscillating field. In Maxwell's language, you are not receiving energy from a distant place. You are participating in a continent-spanning energy field, where thousands of power plants, millions of transformers, and trillions of electrons all oscillate in the same rhythm. Your single switch flip is a very small energy request sent into the grid. The grid responds by adjusting generation at whatever plants are running, sometimes gas turbines, sometimes hydro, sometimes wind or solar. But no matter the source, the energy travels through the field, not through the wires. That explains why the grid can respond in milliseconds when you turn on a light, because everything is connected by the field, not waiting for material particles to travel. When you understand the journey from dam to light bulb in this way, you see that the electrical world no longer operates by the water pipe intuition, but by the language of fields and oscillation. The fact that energy does not require a stream of particles to move, but only an electromagnetic field, opens the door to an even greater revolution than the light in your room, the explosion of information, which has turned Earth into a gigantic brain, with billions of connections transmitting data at nearly the speed of light. No one could see that future more clearly in 1837, when Samuel Morse sent the first telegraph signal over copper wire by closing a switch in Washington and hearing a click from a receiver many miles away. Morse did not understand Maxwell, did not know about electromagnetic fields, had not even conceived of the idea of electrons. He only knew one thing: electric current could carry symbols, and symbols could carry meaning. Morse code, a literal alphabet made of electricity, turned signals into sound and light, and the telegraph became the Victorian Internet. 2 years before the light bulb even existed, humans were already texting across continents by making the field in the wire oscillate in a simple pattern: on off, on off. That was binary. Only 40 years later, in 1876, Alexander Graham Bell took a much bigger step. Instead of sending only discrete signals, he sent the oscillations of sound itself electrically by converting air pressure variations into current oscillations. Bell did not create a stream of sound running through the wire. He simply made the electric field along the wire oscillate in the shape of a voice wave, and when the field reached the other end, it forced the speaker diaphragm to oscillate back into sound. Once again, no electron traveled more than a few millimeters. Only the electromagnetic field did. The telephone was a national-scale field transformer. The world at the time did not yet understand why it worked. But Maxwell had already written the answer in 1864. Electricity can carry waves. Then came 1947. At Bell Labs, when 3 young physicists, John Bardeen, Walter Brattain, and William Shockley, invented the transistor, a device the size of a fingernail that became the foundation of the entire digital age. What made the transistor supremely powerful was that it needed no mechanical mechanism to switch on and off. It used an electric field to control the flow of electrons, meaning it manipulated fields, not matter. A small electric pulse at the gate could turn a large current on or off between source and drain. You can call a transistor a field switch. You can call it an artificial atom. You can also call it the heart of every computer that has ever existed. Computers do not compute with pistons, cables, or gears. They compute with electromagnetic fields controlling electrons. A single transistor knows only 2 states, 0 or 1. A modern smartphone contains tens of billions of transistors, meaning tens of billions of field switches, turning on and off billions of times per second, creating music, images, text, video, maps, and the entire virtual world you live inside with it. But before computers became personal devices, the world witnessed another unforgettable moment in 1969, when researchers at UCLA and Stanford connected 2 computers over a line using a new technology called ARPANET, the precursor to the Internet. They tried to send the word login. The system managed only low before crashing. That was the first moment the Internet spoke, like the birth cry of a new organism. The Internet is humanity's second power grid, a grid of information, and it works for the same reason the electric grid works. Signals do not travel through wires like water in pipes. They propagate through the electromagnetic field in the form of pulses, bits, data packets, routers, fiber optic cables, satellites. All are merely structures that guide electromagnetic energy to the right place. When a data packet travels from New York to Tokyo, it hops through a network of wireless fields, copper wires, lasers, and optical fiber, radio waves from satellites. What really moves is the oscillation of the field, not electrons. The next step in the information explosion came in 2007 with the iPhone. That phone was not just a handheld device. It was a portal into the global electromagnetic grid. The touchscreen works by measuring changes in the electric field when your finger approaches. Wi-Fi is an electromagnetic field oscillating at a few gigahertz. The GPS chip measures the timing of electromagnetic signals from satellites. The camera detects photons, electromagnetic oscillations, striking the sensor. The CPU turns billions of transistors on and off every second using tiny electric fields. Everything you do on a smartphone is an interaction with the electromagnetic field, reading, sending, watching, listening, navigating, learning, entertaining. The entire world has been shrunk into a device the size of your hand, and every part of it operates on the same principle that Morse, Bell, Shockley, and A.R. Pennant sketched out long ago. The electromagnetic field carries information, transmits information, turns information into energy, and energy into information. Today, humanity sends more than 300 billion emails every day, watches billions of videos, streams thousands of hours of live video every minute, and most of it happens in streams of electromagnetic fields invisible to the eye. A tweet, a text message, a video call, a downloaded file, all are vibrations of electrons in place, driven by oscillating fields, broadcast from gigantic data centers, where millions of transistors flicker on and off like fireflies on an artificial summer night. Remember, no single electron travels from sender to receiver. Only the field propagates. Information is precisely a change in the pattern of the field. Electricity did not merely light up the world, it connected the world. It turned the planet into a gigantic nervous system where every human is a neuron capable of sending signals to any corner of the earth in a fraction of a second. From Morse code in 1837 to the telephone in 1876, the transistor in 1947, the internet in 1969, and the smartphone in 2007. The information explosion is not a story of wires, chips, or screens. It is the story of the electromagnetic field, which Maxwell described with 4 equations, and humanity turned into the foundation of the entire 21st century. When you look at the information explosion that electricity has created, you will see an even deeper, bolder, and harder to accept truth than anything we have discussed. The mechanical world you think you are living in is actually just a useful illusion, an intuitive interface constructed by your brain to manipulate a reality that is fundamentally built from electromagnetic fields and quantum particles. Every mechanical force you have ever felt, from the force you use to push a door, to the sensation of your hand touching a table, to the collision between two objects, to the friction that keeps you from slipping. None of them is an independent mechanical force. They are all electromagnetic interactions between electrons in your body and electrons in the surrounding matter. When you place your hand on the table, your electrons do not touch the table. They are repelled by the electric field of the electrons in the table. You feel solidity, but in reality, no surface touches another surface. When you throw a ball, the image of solid blocks transferring momentum through the air is actually electrons in the ball, exchanging virtual photons with electrons in your hand. When you walk, the friction force that Newton described as a mechanical force is entirely electromagnetic repulsion between electrons on the road surface and electrons in the soles of your shoes in the direction opposing slip. The entire world you call mechanical is merely a thick layer of paint covering a deeper electromagnetic reality. This becomes obvious when we reach the Standard Model, the particle model, completed in the 1970s, which describes the entire universe using quantum fields and four fundamental interactions: the strong force, the weak force, gravity, and electromagnetism. The first three govern the nuclear and cosmological world, but virtually everything you experience in daily life, chemistry, heat, light, sound, solidity, friction, atomic structure, is electromagnetic. Electrons hold atoms together electromagnetically. Chemical bonds are electromagnetic. Light is oscillation of the electromagnetic field. Heat is the motion of atoms bound by electromagnetism. Elasticity, hardness, melting point, color, all are consequences of electrons interacting through the electromagnetic field. Without electromagnetism, there is no mechanics, no matter as you know it. This brings us to one of the most beautiful pictures in physics: force equals sign exchange of photons. That is the central truth of quantum electrodynamics. The theory I spent many years developing together with Schwinger and Tomonaga, for which we received the Nobel Prize in 1965. QED says there is no force in the classical sense. There are only electrons continuously exchanging virtual photons. These photons are not the light you see. They exist for extremely short times, just long enough to transmit influence from one electron to another. When you press a computer key, trillions upon trillions of virtual photons are exchanged between electrons in your finger and electrons in the key, producing the reaction force. When you lean against the wall, the force holding you up comes from electromagnetism. When you snap your fingers, pull out a chair, open a door, you are performing QED in everyday life without knowing it. Consider the solidity of matter. Why do atoms have size? Why don't electrons collapse into the nucleus? Why don't objects pass through each other? The answer is not classical mechanics, but the Pauli principle. And QED, electrons occupy distinct quantum states and cannot overlap. Electromagnetism forces them to maintain stable configurations. The probability waves of electrons create a no-entry space. Matter is not solid. It only appears solid because electromagnetism is so overwhelmingly strong. Even the collision between two billiard balls is not two solid spheres smacking into each other, as classical physics describes. It is electrons on the surface of each ball, repelling each other through virtual photons. The world you see is an electromagnetic simulation translated by your brain into a mechanical experience. But that illusion goes even further. Every sense you possess is electromagnetic vision. Photons excite electrons in the retina. Hearing pressure oscillations make air molecules bound electromagnetically vibrate, which then act on the eardrum. Smell and taste. Electrons rearrange when molecules contact receptors. Touch. Electromagnetic forces prevent your electrons from penetrating the electrons of an object. Even thought is electromagnetic. Neurons transmit signals via action potentials. Ions move across cell membranes. All of it is QED at biological speeds. Your brain is an electromagnetic machine, observing an electromagnetic universe. QED is famous for its extraordinary precision. It predicts the electron's magnetic moment in agreement with experiment to 1 part in 10^^2, one of the most accurate achievements in the history of science. That precision leaves us no choice but to accept that the mechanical, solid, touchable world is merely a simplified flat map of a far more complex quantum terrain. You do not live in a mechanical world. You live in a quantum field, and mechanics is merely the user interface, your brain designed to manipulate that field efficiently. Why does our intuition cling so tightly to the mechanical world? Because the brain did not evolve to see virtual photons, quantum fields, or Maxwell's equations. It evolved to throw stones, escape predators, and pick fruit. The real world is too complex, too fast, too small for intuition to grasp. So the brain constructs a more comprehensible mechanical illusion. But when we peel away that illusion, when we see that a hand press or a footstep is merely electrons pushing electrons through virtual photons, the universe suddenly becomes both simpler and more wondrous. Once you become comfortable with the idea that the mechanical world is merely an intuitive interface, masking a deeper electromagnetic reality, you begin to see the universe exactly as Maxwell and Einstein saw it, an invisible ocean of electromagnetic field, constantly oscillating, constantly propagating, constantly interacting. Even when your eyes see nothing but quiet air, if your eyes could see fields, you would see the space around you swimming in radio waves. From low-frequency AM waves around 535 kHz bending through buildings to FM waves 88, 108 megahertz slipping through every wall, to thousands of Wi-Fi streams at 2.4, 5 gigahertz continuously pounding into your body, passing through you, and continuing as though you did not exist. You would see Bluetooth, radar, cell phone signals, all layered on top of each other, like overlapping ocean waves crashing on the same shore. And the strangest thing is that they do not push each other aside, do not compete for space, do not cause electromagnetic traffic jams. They simply pass through one another, as though space was specially designed to allow countless oscillations to coexist. That is the universe in Maxwell's language, where electric and magnetic fields give birth to each other, propagating freely without needing any material medium at all. It was hard to believe in the 19th century, and so in 1887, two physicists, Michelson and Morley, decided to test whether light needed a medium called ether. They used an interferometer to measure the speed of light in different directions as Earth moved through space, and they obtained a shocking result that shook the foundations of physics. There was no change at all. The speed of light was always the same, no matter that Earth was hurtling at 30 kilometers per s around the sun. That not only disproved the ether, but led to one of the most important intellectual leaps in history. Einstein concluded that it was not light that changed, but time and space that changed to keep the speed of light constant. And if you look deeply into the implications, you will see something astonishing. The electromagnetic field needs no medium, because space-time itself is its medium. The field is a property of space, not something added afterward. It does not reside in space, but is part of the structure of space. Once you grasp this, you will never see the world the same way again. You will realize that the phone you hold in your hand is not sending data through the air. It is making the surrounding space oscillate at gigahertz frequencies, that a radio does not receive waves, but merely taps into oscillations that are already filling the space, that radar does not shoot beams, but merely creates ripples in the field, and measures the response, that every Wi-Fi access point in the city is a pebble continuously rippling the surface of space-time. Just by walking through your living room, you are stepping through thousands of field oscillations, radio waves, television signals, mobile signals, countless neighboring Wi-Fi networks, all different expressions of the same electromagnetic field that Maxwell described with his 4 immortal equations. Those oscillations do not merely pass through solids, air, or vacuum. They propagate through the very structure of space itself, needing no carrier, no substrate. And that makes the universe at once utterly empty and utterly full. Empty because there is no matter, yet full because fields are everywhere. If you had electromagnetic eyes, you would see the Wi-Fi routers in your neighborhood forming vibrating field bubbles. You would see FM broadcast towers radiating spherical wave fronts. You would see radar signals sweeping the sky like invisible blades of light. You would see every cell phone as a tiny field source constantly talking to base stations. You would see the entire Earth glowing in the electromagnetic spectrum, like a living creature moving in an endless sea of fields. Why, for more than a century, have students been taught that electricity is electrons flowing through wires like water in a pipe, that electric circuits work like a circulating water system, that conductors transport electrons from one place to another, that a light bulb glows because electrons reach the bulb? It is not because teachers or textbooks refuse to teach the truth. It is because the truth is far too complex to fit into a simplified model designed for students who do not yet have the mathematical foundation. School education completely omits the concept of the electromagnetic field as Maxwell truly described it. It never touches QED, the theory in which electrons interact via virtual photons. It does not mention that electrons are probability clouds rather than tiny solid particles. It does not say that electrical energy travels outside the wire according to the Poynting vector. It does not explain that the solidity of matter is only electromagnetic repulsion. It does not say that light, chemical bonds, friction, and nearly the entire macroscopic world are simply electromagnetism wearing a mechanical disguise. And precisely because those pieces are missing, a wrong but easy to communicate metaphor was adopted. Electricity equals water in a pipe. That metaphor lets you imagine current, voltage, and resistance as water flow, pressure, and valves. But it collapses the moment you apply it to any real phenomenon. Electrons do not flow fast. They drift so slowly that you walk faster than they move. The electric field propagates near the speed of light, while electrons remain almost stationary. Energy travels outside the wire rather than inside it. Electric current does not require a closed loop to deliver energy. Electromagnetic induction has nothing to do with water. Increasing voltage is not like increasing pressure. Electrons are not pushed like water. Wires do not leak electrons. Radio waves are not streams of particles, but propagating field oscillations through vacuum. Another problem is that textbooks completely avoid any accurate description of the electron. The electron is not a tiny marble, as the diagrams show. It is a delocalized quantum field, a probability distribution cloud within the atom. Electrons in a conductor do not run like little balls. They only undergo very small collective oscillations, while the energy travels in the field outside the wire. These facts are true, but extremely difficult to describe without university-level mathematics or quantum mechanics. So the education system chooses to leave them out. The result is that you grow up believing that current flows around the circuit like water in a pipe, when in reality an electric circuit does not require electrons to complete a full loop to transfer energy. Energy is supplied by the field surrounding the wire. The instant the switch closes. School education also completely ignores the truth that light itself is electromagnetism propagating freely, that the electromagnetic field requires no medium, that electric and magnetic fields exchange roles in electromagnetic waves, that chemical bonds are electromagnetic sharing of electrons, that all contact forces are electromagnetic, that QED describes force via virtual photon exchange, and that touch is an electromagnetic illusion, not because the curriculum is wrong, but because it is simplified to the point where it no longer resembles the correct model. The most important thing you need to know is that the education system is forced to build useful but incorrect intuition first, then hope that those who go further into science will break that wrong intuition and rebuild a correct one. The problem is that most people never reach the breaking stage. So they carry the water in a pipe picture for life and try to explain the world with a model that was already outdated before Maxwell's time. That creates the gap between how the real world actually works and how we think it works, between electricity as field and electricity as flowing water, between QED and 7th thick grade physics. And it is precisely that gap that makes most people feel electricity is strange, hard to understand, absurd, because you are trying to use an ancient model to describe a modern phenomenon that the ancient model was never designed to describe. But when you step out of that intuition, when you accept that electricity does not flow but oscillates, that force does not push but exchanges photons, that matter is not solid but shaped by fields, you will see a world that is far more coherent, far simpler, far more beautiful. Once you realize that all popular models of electricity are metaphors, and that the real world operates through an electromagnetic field that permeates all of space, try looking again at the most familiar action in daily life, flipping a light switch, and see what really happens at the fundamental physical level, not the simplified version in textbooks. When your finger presses the switch, you are not sending electrons anywhere. Instead, you are allowing the 120 V electric field of the grid to appear across the conductor leading to the light bulb. The electric field propagates along the wire at nearly the speed of light in copper, while the electrons in the wire barely oscillate in place. Copper is an excellent conductor with resistivity around 1. 68 Packard and Haber 7, mooning electrons in it, can respond very easily to an electric field. But it is the electric field itself that travels fast. The electrons are slow, extremely slow. And when the electric field reaches the bulb, it encounters something completely different from copper wire, a tungsten filament. Tungsten has a dense atomic structure and much higher resistivity. When the electric field tries to force electrons there to move, their motion is strongly impeded, and that resistance converts electromagnetic energy into heat. In a fraction of a millisecond, the filament temperature shoots up to 2,700, 3,000 degrees Celsius, hot enough that electrons in the tungsten atoms are continuously excited, then fall back to lower energy levels and release photons via the QED mechanism. Those photons have wavelengths in the 400, 700 nanometers range. Visible light, the kind your eyes are most sensitive to, and that is why the bulb glows. Everything happens so quickly that you think the light comes on instantly. But in reality, what makes it instant is not that energy travels from the power plant to your home so fast. It is because the electromagnetic field of the grid was already there, right in the walls of your house, right in the wiring, just waiting for a path to act on the tungsten. The switch closes the circuit. The field instantly has a path to act on the electrons, and the bulb lights. No electrons travel from the power plant to the bulb. The electrons in the filament have been sitting there since the bulb was manufactured. The grid does not transport electrons. It transports energy, and that energy travels outside the wire according to the pointing vector, flowing through the space around the wire, directed straight toward the place where the electric and magnetic fields intersect to deliver energy into the load. The conductor only serves to guide the flow of energy, like train tracks shaping the path of a train. But the train does not run inside the tracks. It runs along them. If you replace the copper wire with steel, you would see the bulb glow much more dimly, not because of fewer electrons, but because higher resistance causes more energy to be lost as heat along the way, meaning the electric field has a harder time delivering energy to the bulb. When tungsten reaches 3,000 degrees Celsius, it emits not only visible light, but also infrared. In fact, most of the energy you pay to light the room is converted not into light, but into heat. That is why incandescent bulbs get extremely hot and have low lighting efficiency. But from a physics perspective, it is a masterpiece. Electrons are forced by the electric field to change energy levels and emit photons with a spectrum approximating Planck's law. The most important thing to remember is this: everything that happens when you turn on a light depends on the field, not on a stream of particles. You are not pushing electrons through hundreds of miles of wire from the power plant. You are only connecting the local electrons to the 60 Hertz oscillation rhythm that thousands of turbines maintain in synchrony. The power plant does not send electrons to you. It only makes space oscillate. When you turn on the light, you do not take electricity from the plant. You join an oscillation that already exists throughout the entire grid. When you understand that flipping a light switch is not sending electrons racing hundreds of miles along wires, but forcing local electrons to join the continent-wide electromagnetic field rhythm, you begin to realize a much deeper truth. Humanity is the first and only species on Earth that has learned to deliberately control one of the strongest forces in the universe, the electromagnetic force, which is stronger than gravity, between two electrons, not by a little, but by n hundred times. Yet, instead of being crushed by that absurd power, we learn to bend it, shape it, harness it, turn it into light, sound, motion, data, and even the thoughts running through your mind as you read these words. I know this at the deepest level possible because in 1965 I received the Nobel Prize together with Julian Schwinger and Shinichiro Tomonaga for developing quantum electrodynamics, the theory that describes how electrons and photons interact with astonishing accuracy. The magnetic moment of the electron, predicted by QED, matches experiment to 1 part in 11 trillion, a level of precision no other scientific theory in human history has achieved. QED is not an abstract set of equations written on a blackboard. It is the real story of how everything you call electricity actually works. Why the bulb glows, why matter is solid, why atoms are stable, why you see 400, 700 nanometers, photons from a 3000 degrees Celsius tungsten filament, why iron is magnetic, why electrons do not fall into the nucleus, why you can touch a wall without passing through it. All of it is QED happening at scales smaller than any intuition you can imagine. Looking back at humanity's journey with electromagnetism, from Faraday's magnet spinning experiments in 1831 to Tesla and Westinghouse lighting the Chicago World's Fair in 1893, to Morse sending signals in 1837, to Bell transmitting voice in 1876, to ARPANET sending O in 1969, to the transistor in 1947, and the smartphone in 2007, to the power grid delivering energy to your home in fractions of a millisecond, you will see something marvelous. We did not merely use electricity as a tool. We stepped inside the structure of reality itself, understood how electrons, photons, and fields operate, then used that very language to build modern civilization. And what delights me most is not the power itself, but the attitude that comes with it: curiosity, playfulness, and humility before nature. Because every time you think you have understood everything, nature throws you a new puzzle, and its generosity lies in the fact that every puzzle solved reveals yet another layer of beauty. I once said that the universe does not have to be beautiful by our standards, yet it is. It does not have to be understandable, yet we can understand parts of it. It does not have to cooperate, yet it allows us to manipulate a force of unimaginable strength without burning ourselves up. And that is what fascinates me most. Human curiosity is as powerful as the electromagnetic force, And it is that curiosity that drives civilization forward. If you keep that curiosity, the same curiosity you had when you opened the screw to see what was inside, you will discover that electricity is no longer just a utility. It is a bridge connecting you to the way the universe truly operates. And perhaps the greatest gift nature has given us is not the answers, but the joy of finding them. The joy of realizing that understanding does not make the universe mundane, but makes it more wonderful. Because when you understand electromagnetism, you do not merely see light from a bulb. You see the field itself whispering the structure of the world. Please hit subscribe so you don't miss our next journeys into the wondrous world of physics. See you in the next adventure, where we ask why again and smile when the universe answers.